I'm Tony. We're going to take you on a journey from teaching the babies to teaching the young adults when they leave school, a journey which is called Algebraia.
Hello, everybody. I'm happy to meet you. My name is Wetemba. I'm a mathematics education lecturer at AIMSEC, Stellenbosch.
My name is Caroline. My mission in life is to make maths fun, that every child on earth will love learning mathematics.
Now, what we're going to be doing today is a theme which is about rectangles, areas, and multiplication. And here we have the Macy's Marching Band. Where's the maths? Well, we're going to find maths. And what we see is a rectangle, and you might ask, how many in the band? So how would we find out? Well, we'd look at the shape in the rectangle, but in front of them, we've got the 10 majorettes who are all in red. They don't seem to have instruments, but they're leading the way. And then it's very difficult to see, but in the middle, up the there's two people holding a banner who are in the red uniform, red trousers, and behind them there are two leaders. Now, apart from those, everybody else, there's a few odds and people at the back. They seem to be in columns with 8 people in each behind the leaders at the front. If we were in the street, we could count the number of rows from the front of the marching band to the back. We can see very clearly that there are 8 columns. And then we don't need to do it, but it's just an illustration of how we would find out. We'd multiply the number of rows by the number of columns to find how many people altogether. And then we're bringing in the concept of area, and everybody's got their personal space. And so we're imagining that they each take up the same amount of space on the ground. Not true, but we just assume that's sort of average. And then we've got the area of the rectangle that they make. And so now we have linked the number of players, which is a multiplication of the number of rows and columns. We've linked that to multiplication, and we're linking it to area on the ground of that moving rectangle as the band marches forward. And so are we ready now to march forward on our workshop? Here you see, supposing you have got a group or a class of children, some or all of the children could be arranged in rectangles, and then you could count the numbers of rows and columns and find out how many people there, how many children in the rectangle, and you could also see that you could count, but you could also multiply the number of rows by the number of columns. And then again, children can talk about this, how much space they need. There you see they're stretching out their arms, so they're taking up a certain amount of space, and there's a distance between them from back to front. So we can call that each little square of area on the ground. So again, we're linking up this area. If we want of a rectangle made up of lots of smaller areas, units, and if we want to, the children at the corner could hold a piece of string. This is not essential because you could do this without string, but if you have some string, you can mark the boundaries of this rectangle by the children at the 4 corners holding the string and pull tight between them, and that marks out the area. Just as well, you can imagine the area, and of course you can do quite a lot of work here on multiples and factors by arranging your class, or some of your class arranging themselves in groups. There's a nice idea. We call that people mathematics. It's the sort of mathematics where everybody gets up out of their place. It's good to do this out of doors, and they physically move around into a formation here, and that's part of the thinking. Where are we? And it's people mathematics.
What you're looking at is a square, And that square is made up of small units. We're calling each of those little squares 1 unit of area. This is very powerful. We're interested in how would you use it? So any ideas that you have. So what is the area of the big square? And then you observe that there's broken into smaller rectangles of different sizes. So how is it split up?
As you can see on the slide, from the previous slide, we were given a square which is split into smaller units. And here, we only have dimensions given. The side, it's a square of side 4 plus 1 and side 3 plus 2, and we're required to find the area of the whole shape. How do you find the area of the whole shape? We make use of the subdivisions there, the small squares and rectangles within the bigger rectangle. If you multiply 4 plus 1, multiply that by 2 plus 3 in brackets, that gives us the dimensions which make up this square. The area becomes 5 times 5, which is equal to 25. So the splitting of the square is actually helping us to come up with the area of the bigger square.
It could actually represent something else, and here we're now going to move on with our theme. It could represent 40 by 30, and now we've got 41 by 32, and now we have got a rectangle. So here we have got 41 by 32. Write what the answer is on the chat line. If you can imagine doing that multiplication this way, what you would be multiplying would be adding up the 4 smaller areas. Now it's not to scale. We have got 4 smaller areas to get a total. In green, it's 1200. In the blue rectangle, it's 80. In the mauve rectangle, it's 30. And in the sort of orangey colored, it's 2. So that's 1,312. What we're doing now is showboards, how to involve everyone in your lesson. The beautiful way is a showboard. It's lovely to put that on the back, or just laminate that one sheet of paper which is blank on one side and squares on the other, and then you see these children in this class holding it up with an answer. So it's 2 centimeter squares that work best for this. They need a pen, a dry marker, and they can write things on their showboards. And so you can quickly get feedback and answer from the whole class. And you can see everybody must hold up their showboard. And there's Caroline showing you exactly how to use a showboard. There's a link there for where you can print it.
If you don't have a laminator, you can find a sponsor, maybe somebody in town who's willing to sponsor you, or you can also create them with plastic on paper, stick plastic onto paper, great way of recycling. There's lots of different ways you can do it.
Yeah, and the thing is, if you do have in your nearest town, you do have a print shop, this is not a very expensive thing to get it laminated. It costs a little bit, but it lasts and lasts and lasts and lasts. It's like the old-fashioned slate that people used to have.
Right, on this rectangle, we still move on with the concept of building, with the concept of area. But instead of us using numbers, we have decided to make some girls line up. We have a portion where the girls are lined up, which is the length of the first rectangle on top there, and the boys line up also, such that we have a number of rows. It could be a certain number of girls, a certain number of boys. Then on the other side, we have cymbal players and drummers. We still want to find the area of the whole shape, but coming from the smaller pieces which make up this whole shape. You can see we can actually introduce variables here instead of us using numbers. For girls, we decided let's use letter G, and for boys, let's use letter B. And cymbal players will make use of letter C, and for drummers, we make use of letter D. How do you find the area of this big shape? Building on from the smaller subdivisions of the whole shape. GC in this case will be the number of girls lined up multiplied by the cymbal players. Remember, we said here we're assuming that each small square unit where a person stands, the area is actually a square unit. So on average, we are estimating our area to be the number of girls multiplied by the number of cymbal players, boys by cymbal players, and so forth, as you can see on the diagram. So what will be the total area of this whole shape? It will be the product of G plus B multiplied by C by D. It's actually an opportunity for us to introduce students to variables or to some algebra moving from numbers. But these letters, as we said before, they actually stand for the numbers, which they are familiar with at the beginning.
Imagine the children standing, quite young children, it's not algebra, but they could be standing pretending or actually play, with different instruments. They're making up a band. They can make up bands with different numbers of girls in the columns and boys in the columns and cymbal players and drummers in the rows. And for the older children, a bridge to the algebra there. And here we're talking about a principle of our learning from babyhood right through to old age, and certainly through the school years, it's like a ramp which goes on and on and on forever as we're learning more and more and more. And we need to, it's just what makes life interesting. And we're going to explore that idea throughout this 2 hours because it's all about the spiral of learning curve. But we're talking about Algebraia. And by the time the children leave school, they'll have gone up several layers of this ramp, introducing the rectangles, multiplication and area at different levels. And by the time in the school leaving year, we want them to be able to multiply algebraic expressions and form equations and apply the algebra to solving problems. And so we're going to understand that learning doesn't stop when they leave school. It goes on, the spiral continues. But we do start with the very early years when we'd now like you to think actually about your own experience as a teacher. And you've got a little bit of an idea of this concept that we're developing and how you might think now about how you might introduce that with your own children. You may have a mixed age group, in which case we're providing for you, or if you're teaching 9-year-olds or if you're teaching 14-year-olds, at this moment, we've got some ideas, but you might have your own about how you might use this for the different age groups. So starting with the preschool, it's just an informal understanding of the shape of a rectangle and the area. And then we go on year by year, we're going to talk about what we might be doing with this time once they've started school. We're going to have a connection between counting squares and multiplication. And then when they're this year's 4 to 6, they're sort of roughly what, 9, 10, they're going to be counting the number of elements in a rectangular array and realizing that they can do calculations now with multiplication. By the time you're starting secondary school, years 7 and 8, they should be now understanding the nature of multiplication as repeated addition and the connection to multiplication and area. So this is what we've been building up to with younger children. And now they're going to be able to apply this to long multiplication using place value. And this gives a very easy way of doing multiplication. And then by the time they're 15, 16, they should be thinking about being able to do all these things, applying multiplication to find area of rectangles, but also connecting that to algebra and applications of algebra. And then finally to solving problems, a little bit more complex problems for the older student. We're going to start having explored the possibilities throughout this theme from babyhood, early years through to school leaving. Now we've got some wonderful patterns here we thought we talked about. Here we suggest that you have lots of red and blue squares and you make patterns with them, or rather the young children make patterns with them. And here are some patterns of paving slabs up on the top left, floor tiling and wall tiling. Quite interesting to look at those patterns. On the left, the checker patterns, black and white. If you didn't have the strips between, those are actually the same pattern, and the diagonal effect is simply where you stand to look at them. And so if you've got children, show them these patterns, or you'll go to your shopping mall and you see some paving, you might stand in different places and remark about what the pattern looks like from here. We will give you the resources that you can use and print them, or you can just make your own tiles with scrap cardboard and make patterns with them. On the right, you'll see some lovely colorful patterns, but they're just made of square tiles. And these patterns occur very often in artwork. On the right, you'll see some beadwork with square patterns on them, and some basket work too. I was quite surprised to find that on basket work, but I knew I'd seen it on various artwork and then craft work. And then of course you see it in murals. Many, many patterns are made with square tiling. So I think this is a lovely game that little children can play.
You can also see from the pictures on the left of our slide that these are pictures taken from real situations, real life situations. You can see the tiling of the floors. We are trying to connect reality to what we teach in the classrooms so that kids see value of whatever we're teaching them. The mathematics, the numbers they see, the patterns we talk about, when they relate with real life situations outside, it makes knowledge, something vital for the children.
And of course, the calculation comes into it too, because we've tiled areas in our house and we've had to go to the shop and buy the tiles. So you have to measure the area, you have to work out how many tiles to use. And so there it is, it's coming into a practical application.
Somebody suggested that you can use the sticky back plastic. Absolutely, great idea. Thank you for sharing.
We have had free play with tiling patterns and observing patterns. This is still young children, early years, but now we're going to have something a little bit more formal in the sense of a set challenge or task.
Right, after talking of the tiles, now we're in the classroom. We have prepared some manipulatives. For example, you can see the first row there, we have a picture of tiles which we have made and brought into the classroom. You ask the youngsters, how many tiles can you see? They are able to count 3 tiles. How many rows? 1 row made up of what? Made up of 3. How many red tiles can you see? How many blue tiles can you see? As you ask such questions, they relate issues of colors, tiles, the number of tiles. There's numeracy there. Then we have a bigger picture there, which is also made up of small squares. How many tiles do we see all together in the bigger picture? They can tell us 8, 4 rows, 2, 4 red tiles by 4 blue tiles, you make kids realize that, okay, so these tiles, we can actually form different shapes, and these different shapes, as we will see into the, as we move on to the next slides, we'll be making use of this knowledge we are presenting at this stage to develop the next content we want the learners to know about.
There's a play, but it's actually play with some guidance and instruction. And now we move on to an idea. Now we're years 1 and 2 in school.
If you look at my screen, I've got the sheet that's on the display, it's cut out, and I've got all the pieces cut out. And the idea is it's just a puzzle. At this point, for years 1 and 2, it's just a puzzle. They have to line the pieces up, and edges must match. You can't put this piece on that way, this piece has to go that way, and you can't put this piece on that piece there because the edges don't match, but that piece does fit on there. So you can see the logic. You can start, oh, well, that might be a way to start, and just allow them to fill the rectangle, and it can't go outside the rectangle. That piece can't go there, and that piece can't go there. So you've got to really think about it. Go ahead and solve that puzzle and send us a picture. This is something you can do with your young learners.
Now, in general, whatever the age of the children, even for adults, this is about learning. Whatever the age, when you're trying to do something, it's a good idea to play around with the idea in the first instance. If you're writing poetry, you might sort of put a few words in it and think, oh, that sounds all right. Oh, no, that doesn't. I'll say this instead of that. Free play in the beginning. What can you do with these pieces is where you'd start with this task. And then talk.
And the beauty of these pieces, as the kids are playing with them, imagine that these kids already, they are coming from families or houses where there are tiles. They start connecting those tiles they see with what they are doing here. And in their mind, obviously, they develop those concepts. Also, okay, when I'm tiling a house, this is how I should be bringing those pieces together in order to tile my room or tile my house. And slowly but surely building value in terms of mathematics to these kids.
Brilliant. And then the talk is important because it's communication. It's only by actually communicating that we learn to use the language, to express our ideas, to learn new words. And so in order to get the children talking, the teachers should be asking questions. Every time you want to tell a child something, try to turn what you'd say into not telling them something, but asking them a question. And so they have to think, and they'll say what's in their head. Then we come on to the formal task that Caroline showed you, which was making the rectangle, fitting those pieces into the frame so that the edges must be made to match as you fit them in. And so this is easy. There's no sort of numbers or counting or even formally talking about area. This is just a puzzle because after all, at this stage, we're just talking about years 1 and 2. But when we go on to do something similar with the next year group, we'll be just making it a little bit now for years 3 and 4.
We're still trying to move in a progression manner, in that spiral manner Tony was talking about before. Here, with the 10 pieces, we ask, how many other shapes can you make with these 10 pieces? Let the kids play with the pieces, bring them together edge to edge, and see what other shapes they can form.
And that's still following the same rule that they must match.
Yes. You'll appreciate that from the 4 shapes which are shown there, this is what kids could manage to do. But as an educator, I will tell you, let these kids play and explore as many shapes as possible.
One nice way of doing it is see if you can make a shape that's different to everybody else's shape.
And we thought, how many would there be? And we're not even sure ourselves. We didn't bother to pursue that. So obviously there are lots of possibilities. And one thing I like to do with children, if we've got some wall that we can put a display up, is every time somebody finds a new pattern that nobody's thought of before, we put the new one up on the wall. And so it prompts the children to keep thinking of new possible answers, and it celebrates, it gives them a little bit of a reward when they see what they've done. Their new creation, their new discovery goes up on the wall.
It would be interesting after they obtain their shapes, asking them a question like, is it true that whatever way you arrange these 10 shapes, they will together make the same total area? If so, how can you find this area? Leave that as a puzzle, as a question to the learners to find out how can they get the areas of these particular shapes they are making.
Just from scrap card and coloring it, you can make these 10 pieces quite quickly, or for older children, you know, under your guidance, they can make their own, color them, and then they can do these mathematical tasks.
Sarah Baziwe said you can use coloured paper and cut out coloured paper, and then you can stick that coloured paper onto cardboard.
And of course, you won't do these tasks every year, but even if they've done them before, you're going to be adding value each time they meet the same idea again. And of course, you're going to be doing multiplication when you're thinking about the area of a rectangle, but then you're going to be realizing that area and multiplication of two numbers is not the same. It's areas of rectangles, and these shapes that we've illustrated here are actually different shapes, but they have the same area. This is years 3 and 4. What would we do a little bit differently if we moved on to years 5 and 6? Supposing you are teaching years 5 and 6, or you think your learners are ready for just a little bit more, then now let them make their own shape. Give them the scrap card or whatever. Let them work in pairs. Of course, to do this, they'll need some scissors. Let them try to make these squares. So if they start on other shapes, if they start off with the rectangle can be any dimensions at all, okay? That doesn't matter what it is. So we did give you some which you could print and cut out, but they don't have to be the same. They do have to have certain properties. And start with the rectangles, cut out your rectangles. Each of these groups can cut out a different rectangle and don't specify what it is. And then how do they decide on the squares? So when they make the squares, the smaller squares have to match the shorter edge of the rectangle. We call that 1 unit. And the bigger squares have got to have a length and breadth. They must match the longer edge of the rectangle.
If you look at where I am, I've got them as well in my box cut out.
Yes, and so it doesn't matter what X is. This is the point. We should be understanding this arrangement, these mathematical properties apply, the fitting into a rectangle, and everything we've been talking about applies for different values of X. And so what we're actually doing is talking about these shapes. As before, we were going to be asking the children how many other shapes can they make. Show me what you can do with these 10 shapes, using them all, making different shapes, using the rule all the time that they must be matching edge to edge. And that means if it's 1 unit, matching it against a 1 unit length, and if it's X units, matching it against an X unit. So just as with the boys and the girls, the B's and the G's, and the cymbal players and the drummers, we use letters just as a name, like my name's Tony and Temba's name's Temba, okay? We're just using the letters as names. But Of course, there are quite a few Tonys, not that many, but a few. You can have the one name applying to different people. You can have X applying here to different edge lengths. And we're just using these letters, the algebra, if you like, but it's not algebra. We're just giving the idea that it can represent different lengths so that it's different areas. So as we remember what we have been doing right from babies playing with these square tiles, children of any age arranging themselves, getting up, doing this outside, arranging themselves in rectangles, linking the area on the ground, on the space, paper to area, multiplying lengths by breadths to get area of rectangles, thinking about the fact that if we have these 10 pieces, whatever we do with them, they are going to always keep the same area. They're not stretchy material. We're linking the area and the multiplication and the concept of rectangles, multiplication, area, and finally we're going to bring in the algebra. So there's quite a few challenges here, a lot of free exploration possible for the children, but this is really so important because this concept of multiplication. And we're going to give you a challenge to see what you think about this activity of working out long multiplication by a different method of using the areas of the smaller parts of a shape of a rectangle and working out areas, but at the same time doing long multiplication. So the idea is that if you're teaching or at home with preschoolers, then you can start playing with these tiles. And so if that's you, if you're doing that, then if you're a teacher of older children, you might have young children at home, you can use these ideas with preschoolers, okay? And you're building something. We talked about the spiral curriculum. If you're working with 4 or 5-year-olds, you're building something that's going to be valuable to them later on. And then if you happen to be teaching 6, 7, 8-year-olds, then we've presented the simpler ideas. They are using these square tiles, making areas, using these tiles that we've showed you. And then if it's 9, 10, 11-year-olds still in primary school, that's where we are now with the slide you see. We've now got the children making the shapes, the children thinking about fitting the shapes together, linking area multiplication, and beginning to name variables with letters as you would in algebra, preparing them for secondary school. After the break, we are going to be introducing the same theme. Again, we're on this spiral ramp of learning, and we're going to be introducing what you would do if you were teaching older children. And so because on this one theme, there's some activities everybody can do, but at their own level. This is suitable for a mixed age family at home or a mixed age group in a class, as I've just described.
When you say years, think grades, more or less. It's going to be more or less the same, give or take a year. Mary Ocheng says she likes the idea of building up the idea from an array of people so children can easily identify with that.
Mm-hmm. And you can do it with a mixed age group too. It doesn't matter. They don't all have to be the same age. If you think about the marching band, then they can pretend that they are members of the marching band, and that's what distinguishes some of the rows from other rows in your array.
If you realize our slide, our year 5 and 6 learners, they are in their transit to higher grades, secondary school. And if you check here, we deliberately use the same puzzles of these 10 pieces, but this time we've decided, can we put some measures or dimensions to these small pieces? Look at the blue one, for instance, we decided, let's label it X by X. And by doing that, obviously, we're slowly bringing the idea of, variables, which lead us into algebra. Then we have the X by 1, then the 1 by 1. And if you check those three colors, blue, brown, and green, all the other pieces, they are of the same dimensions. So with those 10 pieces, fit them in. Definitely whatever rectangle you will find, you can tell us the length of that rectangle in terms of X and the units. And what is the width of the rectangle? From there, how do you find the area of the rectangle? We have brought some algebra without directly teaching algebra at this particular level.
This is a serious mathematical health warning, and that when you talk about area, it isn't the length times the breadth. It is the length times the breadth of a rectangle or a square, but it isn't just the length times the breadth. So if you ever say area, you talk about the shape. You must talk about the shape. Think about it. What's the area of a triangle? And what is the area of a circle? Always, if you say length times breadth, say area of rectangle. That's the warning.
No question, what is area? And people say length times breadth. And I say, oh, no. No, I don't say no, but I say, oh, do you mean the area of a rectangle? Or do you mean, what's the area of a square? What's the area of a circle? What we would like you to think about and try and do is to work out here what 462 by 312 is using this rectangle. How would you use this rectangle? Think of the 460 and 2 along one edge and what you're going to put on the other edges, and think of the 9 different products here, 9 different areas, and finally work out the sum. And do it by doing 9 very simple multiplications. It's 3 by 4, but if it's 300 by 400, it's 120,000. And it's 3 by 6, which is 18. Wasn't that easy? But this time it's 300 by 60, so it's 18,000. And it's 300 by 2, which is 600. But we're looking at 312. So you have more work to do to find the other 6 areas. And of course, you're only multiplying single digits. But here it's a wonderful way to reinforce ideas of place value, hundreds, tens, and units. It's a simple representation of multiplication by area, because we've got little rectangles inside the big rectangle. We've got a link between multiplication and area to do the calculation. No algebra yet, but once we begin to generalize it, we'll have some algebra. There you go, you add all those totals, and it's a lovely number. I like 144,144 is the answer. A neat way to do long multiplication. So,
and I've done it on my show board, my little show board, and you can see, you can see very quickly, if everybody shows up their show board, how they've done it.
And I love that. Hold it up again, Caroline, because we're using these two-way tables a lot when we teach probability in secondary school. And that's exactly what Caroline's showing you for a different purpose, but we're going to be using it again. There's same idea where she's put the totals across and the totals down, and finally, whether you go down or across, you get the final total, 144,144 in the bottom right-hand corner. Now then, we're making a proper start on our secondary maths, the introduction about Algebraia for secondary school. We're going to show you this slide again. the Macy's Great American Marching Band. And we're showing you this because the people in the band are in the middle. The main number of them are arranged in a rectangle. And if we ask how many of them are in the band, well, if we start counting, we can, if we're on the street, it would be easier to do the counting. But basically in that block of people in the middle, we would multiply the number of rows by the number of columns to get the number of people. And the link with area is the personal space. Everybody there is taking up a certain amount of space, and that's the area. So if we imagine each person occupying one square unit of area, the number of people in the rectangle is the same as the area of the rectangle in square units. So you could do that with your own class. You could take them outside, and some or all of the class could make themselves into a rectangular, we call this an array in mathematics. They can make themselves into a rectangular formation, and you can talk about all the things we've just been mentioning. So there we go. Now, we also talked about the spiral of learning. Now, if you think about it, what we do in school, we revisit the same idea over and over again. And when we come to something to teach today, we feel that the children ought to remember what they've done about this topic in the past. And we hope they'll remember what they've done, and we build on what they know. And this spiral of learning starts off when children are born and they start to look around, and it goes on, and little children preschool are very curious and interested in learning. They teach themselves to walk. Nobody teaches them that. They're very curious. When they go into school, they've been on this spiral, and we hope it continues smoothly so that they're learning more and more year by year. And the spiral continues, and when you're in your 80s or 90s, life is still interesting, believe me, because there's always something new to learn. So it doesn't stop when they leave school, but this is the idea about what's happening in secondary school. Well, no, what's happening from babyhood right through to the year they leave school. They start off with just this basic idea about shape, and then a connection between counting squares and multiplication. And then as they go on year from year, and as their teachers introduce them again to a little bit more maths, they will then begin to understand the nature of multiplication as a addition. It's adding the number in each row again and again and again and again. But the most efficient way is to do it by actually multiplying, and the application of long multiplication, as we've just seen, using place value. And then by years 9 and 10, they're applying this to algebra, connecting it to algebra and applications of algebra. And by the time they're leaving school, they're using the same ideas again, and now using algebraic multiplication and solving equations, and then applying the algebra to solving quite simple problems, solving the equation, but then maybe more complex problems later on. So
Noko says, this is interesting, multiplying by breaking up numbers. It may be easy for our learners to understand.
The other idea in terms of multiplying numbers using shapes, the reason why we thought of let's introduce geometry also, so that we show connections between levels. Imagine a rectangle with numbers on the sides, then a rectangle with some letters, and the concept of geometry mixing with algebra, that make sense to our learners to see the kind of connection. We might be teaching these small topics in isolation, but at the end of the day, they feed on each other. For you to say you have really acquired knowledge in a particular discipline, there is a progression in a spiral form. And this spiral form really, it's a universal thing. Even as adults, we find ourselves growing every day in terms of knowledge. There is no way that spiral thing can be constant at a particular stage. Because when you reach that level, it means you are no longer learning anything, you know.
And the other thing is, if you have a learner who's maybe a little bit older but doesn't understand one of the activities or even several of the activities, and they may be falling behind, then go back down the spiral. These activities we're doing every month, go back down the spiral and start lower down and start building up again. And it's surprising how quickly they will pick it up.
Year 7 is typically the start of secondary mathematics. Extraordinarily, in some countries, grade 7 is still in primary school, but they call it senior phase, and it's now secondary mathematics. But we're now on this brink anyway, just over into secondary mathematics. And now we'd have the learners draw their own shapes, choosing the values for 1 unit and their own lengths for X, and they cut out these shapes from a scrap card, and then they'd solve the puzzle by making a rectangle with the 10 pieces, matching them edge to edge. They'd talk about the different shapes and their areas, and how many other shapes they can make with the same 10 pieces, not rectangles now. The first puzzle is make a rectangle, and then after that, the next challenge is, okay, you've made a rectangle. Are there different ways you can make this rectangle? And then after that, can you make different shapes? Okay. And does it work with this group's shapes where they have chosen their blue square to be something of the order of 3 or 4 centimeters by 3, and another group who've chosen make their blue rectangle rather bigger. They might be 7 by 7, and the other shapes correspondingly. Does it work out, whatever value X takes? And then we're into algebra, really, because that's introducing the X as a variable. And we're also going to think about, ask the children questions, get them to think about the fact that putting these X squared square units together, because there are 2 blues, so it's 2X squared, putting the green square units together. There are each 1 square unit of area, and there are 3 of them, and 5 of the rectangles. So there's lots to do there with your year 7, and especially if they're meeting this for the first time. And then what next?
I've made these shapes double-sided so that they are basically not, it's an interesting activity. So if you get your learners to use these 4 shapes, and can they find any others that make a rectangle? Are these the same? Are they different? And I've made them match. So the green squares are together there, the blue squares are front and back, but are they the same? We're looking for reflections. So we've got, what is the reflection of this shape? You can see, and this is just a cheap little mirror, and you can see the reflection of that. You could turn that around and see the reflection that way. You can even turn it that way. Of course, you've got the power to do that. And you can really get, now, is it the same if I now turn it over and turn it around the other way? Is it the same? And then what about these other ones? Which of these are the same and which of these are different by showing the reflections? Now, we've got reflections in different ways. We've got the lateral reflections, which you see on there, but we've also got rotations. So starting with the original one, is that the original shape that we had? It's blue. This is it. You've also got, if you rotate it around that point of rotation, you get that. Now, is that a shape that we got from any of the reflections, or is that not the shape? Is it the same? Is it different? In what way is it the same, and in what way is it different? And you can if you rotate it by 90 degrees, you can see what rotated by 180 degrees. You can really have a good play with this. And as I say, I've got them back and front, and I've got the green matching the green, the rectangles matching the rectangles, and the blue matching the blue for all the different shapes on the sheet that's on the screen. And that's a nice activity in of itself. So,
Thank you, Caroline. I think that's
you're welcome.
Beautifully. And if you don't just demonstrate it, but if you can let the children do this for themselves in groups and or in pairs, and actually ask some questions so that they notice these things. And believe me, this whole question of transformation geometry is a huge and important area of mathematics and its applications. There is a lot of work done on transformation geometry. Physics is all about groups at the higher level, particle physics. It's about understanding different groups, and what's different about their groups is the symmetries. The symmetries are these translations and reflections and rotations. So the transformation geometry is something we meet in artwork. We meet when we look at ourselves in the mirror, when we look at our two hands and realize they're reflections of each other. It's part of our experience, but it's also part of higher mathematics, and it's part of the application. It's used and developed in the applications of mathematics in physics and in other crystallography as well. So, but here we have got one solution, but we've got different versions of the same solution by reflecting it and rotating it.
And you can get your learners to do the experiment and draw it out so that they really get to grips with it.
I'm sure you'll realize the beauty of these puzzles from where we're coming from up to the stage where we are now. See how they are now taking us into transformations. Talk of reflection of one rectangle on the other, talk of rotation, talk of translation. So these shapes, as we know, these are identities. It's actually going to bring us to another concept where we'll find out whether these particular shapes these learners have managed to build, are they having the same area? That kind of connection makes it so beautiful to expose to the learners.
And the next one goes back to numbers. We've got 4 numbers. You've got the same 4 numbers, 7, 2, 5, and 3. And we've got 4 answers, and we'd love you to put in the comments, what is the answer of those 4 numbers? Which is the one that matches the first one? And go down and do those. And this is a really powerful activity that you can do with your learners. If there's any confusion, any misunderstanding, it's very easy to spot by doing these kind of activities. And then you can help correct it.
So we put 1 arrow in now. 7 plus 2 is 9, 5 plus 3 is 8, 9 8s are 72.
You can use your showboards to see everyone's result at the same time, so you don't have people calling out.
So they can match the expression with the value and realize that by putting in the brackets there, they do change the calculation, but it should be second nature to actually do these calculations.
This is actually a really powerful activity to find out where misconceptions are, where the learners are confused. And then once they've got it straight, then you keep using this activity to give them the practice in a fun way so that it's not a tiresome activity.
Now here, when they multiply 2 by 5, they get 10. And they do the multiplication first because that's what you do. And then, of course, adding the 7 and the 3 makes your 10 plus 10 is 20. And finally, the last one, because of the brackets, you have your 8 multiplied by 2, which is 16 and add 7 gets you there 23.
And then we reveal the acronym of BIDMAS or BODMAS. So BIDMAS comes out naturally rather than it's something you have to learn and teach and memorize. It's not the best way of doing it. The best way is to understand what you're doing.
So now we're moving on to years 8 and 9. These are middle of secondary school, and you might be introducing this for the first time.
Right, we carry on playing with the 10 pieces we have been moving with. This time, remember in the previous slide, we said this blue square will be side x by x, where x can be any number. It can be 3 centimeters by 3 centimeters or 3, whatever dimensions you give. The area of the brown one, it's x by 1 unit. Then the green is 1 unit by 1 unit. Right, with all these pieces, which have known areas after giving dimensions to the small pieces, let's still try and build a shape or a rectangle rather from the small pieces. The way we've been building before, the difference of course now is that we have known dimensions. They will come up with different shapes here and there, but all the shapes they will come up with here, we are insisting they should form a rectangle. You realize that the rectangles they will come up with, if you remember the slide where Caroline was talking of the transformations, a rotation, a reflection, and so forth, they will get different rectangles, but all these rectangles, because they are identities, they will be giving us the same area. We're still trying to reach a stage where the learners are able to find the area of this particular rectangle, even if they are given variables like x. You can see from the shape which is given there, we have 3 green ones, 2 brown ones, underneath 3 green ones, that is with areas x, 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 and so forth. So at the end, ask these learners, what is the area of the whole rectangle? Surely from the small pieces they are able to tell, or from the dimensions as given on the rectangle there, where they can see where is 2x plus 3 coming from? Where is x plus 1 coming from? We are bringing that visually to them through use of geometrical shapes. And like I said, they will obviously obtain different rectangles which are identical. And asking them, what is the area of each? We are all bound to find learners giving us the same area. And this makes us appreciate that whatever rectangle you get, the area is conserved because it's coming from the same pieces, squares and rectangles, which form up this big rectangle. And that's brings us to a very important concept in mathematics, where we say there's conservation of area. Obviously, that conservation of area is seen through fitting these pieces into the bigger one. Can we move on?
Well, I think we've got,
maybe you have
right, we've got this algebra now, multiplying 2 binomial expressions. We've made it concrete, as Tamba's been explaining, and now it's actually can be just algebra, and it works with any 2 binomial expressions. In this case, it's 2x squared is 2x times x, and we see that as 2x times 1 in brown and 3 times x, giving 2x plus 3x equals 5x in the peach color or orangey or browny color. And then 3 times 1, the units at the end in green. But this will work for any 2 binomials. And in fact, you can have 2 binomials multiplied by a trinomial, and you can do any combination of different algebraic expressions, but breaking it down by the powers of x and do it in the same way. And it's a really easy way to conceptualize now the multiplication of algebraic expressions, just as we did it for hundreds, tens, and units, and just tens and units in just number work. So now we're going to move on to an idea about teaching, which is important, and that is teachers should all the time be trying to be getting the children to think, but not just listen to them, and asking questions, and we call those key questions, so that the children don't just give one answer, they give an answer with a reason, and you're helping them, guiding their learning. It's not the old-fashioned tell and listen to me and I'll tell you, I'll explain it, you remember what I said. Not that sort of teaching anymore. So Caroline, talk about the key questions.
The key questions are critical to help the learners learn for themselves. And that's the most powerful way. Then they understand it and they can recreate it. Now, every single activity on the Aiming High website that Tony's created and other people such as Temba have created have key questions. So go to the Aiming High website, search for the thing you're looking for the subject you're looking for, and within each of those activities, the teacher notes, home learning and inclusion guides, you will find key questions. So let's use this as an example. You always want to be thinking of your own key questions, and please do put in the comments anything you can think of we could add to this list. So looking at the first one, this would be the first key question. Show me how to make a rectangle with 10 pieces. You've got the 10 pieces. Everyone has their own 10 pieces because they're easy to cut out from paper. And literally show me. You walk around the room and see what they're doing. And if maybe someone hasn't understood that it's making a rectangle, then that's the moment where you say, what shape is a rectangle? That sort of thing. And you're just correcting by observing what they're doing. And then you only have to talk to the people that you can see any misconceptions from what they're doing. So, show me how to subdivide the rectangle into 4 parts and find the 4 areas. Well, in this case, we've got the X's in, but you can also do it with younger learners, giving it, you can use X or you can use numbers, and divide it into 4 parts and the 4 areas. And it depends on the age, whether you're using numbers or letters. And literally identify the area of each rectangle that they make. And they might not only make they might change the rectangles if they want to. You can play with it because the area is still going to be the same, but let them realize that. And then so they've made different shapes, and everyone, you can take pictures or have a show and tell. Everyone shows their different shapes. What do you notice about the areas of all the different shapes, and allow the learners to notice what are the similarities and what are the differences. Now we're going into numbers, we're going into the what we did during the break. Give this as an example. This is now we're going to say, show me how you would draw a rectangle to multiply 28 by 34. We've got 28 by 34 here as the example. And then they can do it on the rectangle and then write it out so they can very clearly see how those numbers with the tens and the units, the hundreds, tens and units, work together to add up to the final answer. So it's not just a routine, it's not just rote, it's not just a procedure. They actually understand how they get from 29 times 34 to 952. And then with the letters, with algebra, it's just a natural progression. So algebra doesn't have to be scary, it doesn't have to be a mystery, it isn't. Using this activity, you will create learners who are not mystified and scared of algebra. So, and you want to multiply P plus Q, okay, that's the same as 30 plus 4, by R plus S, that's the same as 20 plus 8, it's equivalent. And you put the multiplications within the squares and then add them all together. And you have the answer. So in that way, find the products of the two expressions, but you're not telling them what to do. You're saying, just read the question, you'll see. Let's say you need to multiply it. Show me the rectangle, then find the 4 areas, and then find the product of the two expressions. But if you can, let them do it, observe what they're doing, and then maybe ask some more more specific key questions as you're observing, as you're walking around the room. Or if they can't walk around the room, some classes are very, very full, use the showboards and get them to show you so you can have a very quick look-see. I say you can see what they're thinking and you can spot the confusions and the misconceptions.
And we call them key questions because, you know, a key unlocks something that was locked before. We also talk about sometimes, I've got a block, I don't understand that. You know, it's shut to me, it's a closed door, I can't understand it. What the key question does, it's different from you explaining it to the child, okay? So they understand. It's different. It's using a key to turn that lock and open that door. So they, now they understand. It's opening something to the children, not by explaining it, as a teacher could explain it very well, I'm sure, but that might not help because the child might not still quite get it. But the key is what gets the child to do something, and by actually doing something helps them to think, yes, I see what's going on. I can do this now. And so it's the next step in the learning. It's the key to opening that door to understanding and the next step. And so we're now going to move on to think about these showboards that we've mentioned several times. And we're showing this picture of the children holding up their showboards with an answer on them. This is quite a small group of children, but I've seen this done with a class of 80 or 90 children packed into a room, and everybody is holding up their showboard to show their answer. And the teacher, you see, a typical way of teaching is for the teacher to say, to ask a question and expect the children to put up their hands if they know the answer. And some children put up their hands and others don't. And the teacher in the old-fashioned, long ago sort of teaching would then call on a child by name and they would give an answer. And the teacher, after asking a few questions, would think, everybody understands this. Some of the children weren't even thinking. They were thinking about something they did yesterday, they watched on television, or
noticed a bird outside the window.
Yeah, they could be thinking anything. And they'll only start thinking once you ask them, okay? So by using this showboard, you are asking every child, and every child has to hold it up. And they'll be in trouble if they don't hold it up. And if they hold it up with something wrong, okay, that's fine. They've done something. If it's wrong, well, you can help them get it right. But if you don't know whether they're even thinking, you won't be able to help them. So the showboard is brilliant. And we're actually suggesting here you use it for assessment. This is not like setting a test, but it is like setting a test, if you see what I mean. But it's quick and easy to do it, because what you want to know is, can they do this algebraic multiplication? So if you get them to write it very large on a showboard so that you can see it, then you can look around the class and you can take a few minutes. And Caroline,
There you go, Tony. I've done it.
Oh, well done. What have you done, Caroline?
I've got 3x plus 2, 4x plus 5.
Right. So okay. So would you like to write the 4 areas in there? And then you've got, Caroline, what have you got? You've got 3 separate from your x plus 2, but isn't it 3x?
Oh, 3x. Okay, right. Got it. Okay, 3x. Oh, yeah. That's 4x. Okay, like that. Is that the one?
Oh, well done, Caroline.
Okay. All right. Oh my goodness. And now I've got to multiply them out.
Yes.
Let's see if I can get this one This one. Oh, that's great. I hadn't understood that before. Now I understand it. This is called role playing. I think I got that right. I've actually
3x times 4x is 12x squared. Well done, Caroline. And 4x times 2 is 8x. And 5 times 3x, or 3x times 5 is 15x. And what, oh, yes.
I'm just going to simulate another error to see how Tony handles it.
Okay. What did you do with the 5 and the 2, Caroline?
Well, 5 and 2 is 7.
What were you supposed to do with the 5 and the 2?
Oh, you said multiply. That's right. I forgot because I had the plus signs in front of them. Okay. Yes, of course. Multiply them. Okay. Right. Okay. Oh, I know what to do now. Oh, I think I can do it now. Oh, there. Is that the answer? Have I got it?
Oh, just lower it a bit, Caroline. I can only see a bit. Oh, no, I can see it. 12x squared plus 8x plus 15x plus 10. And well done, Caroline. Well done. Now, can you do something with your expression that you've written on the bottom there with those 2 middle terms? What can you do with the 2 middle terms on the bottom?
2 middle terms. I've got 12x squared. Oh, I've got 15x's and I've got 8x's. So actually I've got more x's. Oh, okay. Okay, right. All right then. So I can put those together. And now I've deliberately made another little mistake because that some people just, like I'm one of them, that makes little mistakes and then you've got to correct it and then it's like, okay, so that's not 100%.
Caroline and I are simulating or role playing this, but the thing is that you yes, 23x in the middle. Yes, so basically you're going to ask your class to do this on a showboard, and the beauty of the fact that they can erase or rub out something they want to change or rub the whole thing clean to start again to put something new on the board means that you can very quickly see from looking around the class who's got the right answer. You might write something on the boards to reflect back to them what they're showing you. You can use these show boards to help them to work something out and then to show you so you can check whether they can do it. So it's a really good way.
And we've got some we've got some comments here. So Mary commented that the children are also able to see what their classmates have done and learn from each other and learn from each other's mistakes. Lillian said the showboard method is super as all learners will be engaged and active participation is enhanced. Even when there are problems, they may be easily detected and solved immediately. And then Sarah Baziwe from Uganda, learners love it as well. It is a sort of a competition and they can easily correct themselves. Fetole loves it. Fetole says the role play is powerful. And you can use the role play in class. You don't have to, you yourself can role play making mistakes so that you can demonstrate to your learners how to respond when they do.
And the whole thing is that mistakes are just learning experiences. Now we need to move on, and Tembe, you're going to talk about, this is upper secondary, this is the older learners.
Yeah, now with the older learners at secondary school, and you'll appreciate the progression we have made from pre-primary playing with rectangles until we reach where we are now. If you relate what we are seeing on the slide, we have a rectangle whose sides are 3x plus 2 by x plus 3. And quickly relating to what Caroline and and my other colleague, Tony, were discussing in the previous slide, you realize that, okay, I have dimensions given in a geometrical form. I need to find the area of this rectangle. How do I get the area? The question says, the area of a rectangle is 66 square meters. Find the value of X. You know, I'm given a numerical value of the area. I also have a geometrical shape where the dimensions of the rectangle are given in geometrical form. And with all what we've been discussing before, students are bound to think, okay, what if I multiply 3x plus 2 by x plus 3? What is it that I'm calculating there? They will appreciate that they're actually finding the area. Multiply out those two numbers, you get 3x squared plus 11x plus 6. But we are told that the area of this particular rectangle is numerically equal to the value 66. You know, the idea of equating comes in. Obviously, we don't have to tell them, but it will just come natural that the 66 is equal to the area of the rectangle whose sides are 3x plus 2 by x plus 3. Then once they equate, you know, expanding these brackets, this is what we have been discussing in the previous slide. We'll get 3x squared plus 11x plus 6 being equal to 66. How do we find X? Because our task is to find the value of X here. See what is happening on the next step. We find ourselves having 3x squared plus 11x minus 60 equal to 0. The challenge at this level obviously will be to come up with, you know, the idea of factorizing, but through some trial and error, because we have been multiplying bracket by another bracket, you will find learners opening, closing, open, close brackets, or some they will think, but 11x, I can make it from a 20x minus 9x. So if I add the negative x, 9x to 20x, I get 11. And check how I've grouped 3x squared minus 9x plus 20x, because minus 9x plus 20x is actually this value 11x here. So that idea of splitting these two, or rather building 11x from minus 9x and 20x, it's actually a skill which comes through solving problems of this nature as you work with kids. Then they will realize that looking at these two terms through grouping, we can factor out a common term where we have 3x multiplying the common term x minus 3, 20 multiplying the common term x minus 3, and then that gives us 3x plus 20 multiplying x minus 3 equated to 0. Then we are still interested in solving for x. And at this level, they are able to equate one product to 0 and try to solve for the unknown variable. In this case, we will find that there are two solutions, but because they are conscious that we are dealing with dimensions of a rectangle, and a dimension of a rectangle can never be a negative value. So one of those possible solutions to the equation, we throw it away because of the nature of the question. So x equal to 3 can be the only solution in this case. So once we get that x equal to 3 is the value of x, it means we can actually find the sides of this rectangle, the length and the width. How do we get that? Let students discover that through substituting that value of x in the expression 3x plus 2 and x plus 1 gives us the dimension 11 and 6. And when you get those dimensions, multiply those two numbers, you will for sure realize they give us what? That 66 which we are given there. If one asks, find the perimeter of this particular shape, we know that perimeter, it is the distance right around the geometrical shape, in this case, the rectangle. And that gives us a perimeter of 34. Suppose the problem was changed to, I cannot see that. Suppose the problem was changed to ask what length of fencing would be needed to make the square enclosure of the same area. You see, this is a different style of asking the same question, you know, and these are the kind of word problems which we meet, and we need to handle them and make use of the algebra to solve such word problems. And most of these word problems are real type of situations we meet in real life. You know, talking of the issue of what kind of fence, how much length of fence do I need to fence this particular dam? This very question which made us develop the whole presentation we've given you. We're now thinking, how do we reach here from preschool? How do we build the knowledge from preschool, grade 1, I mean, year 1, year 2, year 3, up to this particular level? You know, as educators, just look at this. When we started off with this question, we started expanding our thinking of how do we develop knowledge from the lower grades until we reach this particular level. And from here, those who go to maybe tertiary and so forth, you might be asked, what is the maximum possible length of fence we need? When you talk of maximum possible, we're now thinking of what? Of maximizing or issues of minimizing. And for the grade 12s, they meet some of these challenges when they are dealing with calculus, you know, which prepares them for university stuff. And look at the kind of connections we're bringing in one particular example.
And this last question is a generalization, as Temba's saying. And so the maximizing idea can be, you know, what is the, if you have a certain length of fencing, what is the maximum area that you can enclose with it? And then you can even generalize that. If you've got a rectangle and cut out squares at the corner and make it into a box, what is the maximum volume of the box that you can make? So questions don't stop with one answer. The answer isn't the goal, it's learning that's the goal. I have a wonderful colleague, he specializes in early years, and he asks, what if? What if? Just those two simple words. So you reach an answer and everybody's smiling because we've got the answer. And then what if we change something in this question? We make it a little bit different. So we're making a generalization. And he does this so beautifully that he has the children, he says to them, anybody like to suggest a what if? And what they're doing is what people who are mathematicians on the edge of research, finding out new mathematics that nobody's ever thought of before. And how do they do that? They're doing it by generalizing what is known and changing something and pushing the boundaries out to a new what if. And that's what I hope you're doing with the learners that you teach. You know you have your school syllabus, but just when you can fit it in, everybody's pressured about getting through what you've got to teach for the exam, but to teach is teaching for the exam. Education is teaching children to think and to think beyond that exam. Not necessarily anything more difficult, but to just use those brains they've got to do what human beings are so good at, being creative. Because in this day and age, that's what we need to give our children when they leave school, because machines do so much of the simple processes. This is our final message to you. There's a huge collection of free lesson resources on the Aiming High website. And go there, explore, you'll find you can search by the topic you're going to be teaching next week and find what we've got that's on offer to you. Creative Commons means that you can copy and change it. You can download worksheets for your children. The AIMSEC app there, you can download the resources and use them on your phone or computer offline. You don't need to be connected to the internet once you've downloaded the resource. Now, on the same website, we've got collaborative professional development. And if you've been on an AIMSEC course, you'll know that what we mean by that, collaborative professional development. What we mean about that is that you as teachers organize workshops with other teachers. You don't teach your teachers, you sit down together and explore new ideas together for teaching, ideas for what the activities that the children in your class can do. The AIMSEC website is a different website to the Aiming High website, but they both belong to AIMSEC. We'll stay around a little bit longer if anybody wants to say hello or to ask a question or to make a comment. It's all yours.
Mariam has said, I will apply what I learned today to help learners who are stuck down the spiral staircase and bring them on the level they need to be. Mary from Kenya said, base multiplication of binomials on area.
The first question, I saw the usual with my learners are using the name Otmas, which is B-O, but now I saw B-I, so I want a clarity with that one. What is
well, I can answer that, Shangisa. We weren't spending much time on it because it isn't worth the time spent on it. It's much better that you learn the process and understand what you do rather than learn a sort of little rhyme or bidmas. But bodmas, O is for order, and it's not a word which obviously means the little power up in the air, whereas index definitely means the power up in the air. So whether it's the O in bodmas or the I in bidmas, it's the little power, it's the exponent. And it's annoying that there are several different words for the exponent. It's called the exponent, the power, the index, and then in your bodmas, which some people use, personally, I never ever use any of these mnemonics, and teachers think I'm mad, but because I just much get it better to understand. So you do it because you understand it rather than you've remembered some soccer tour or something. Okay, but sorry about that rant, but it's the I and the O both stand for the little power or exponent. Shangisa, did you want to ask something else?
Yes, like the other question with regard to transformation. There is a lot of transformation in the grade 8 and the grade 9. So my issue is, or my problem is, there is no transformation in our grade 10. So what is the importance? So how would it help our learners? Like I'm just thinking of a chapter that will be spending much of your time and they are not going to go further with it. Because in grade 10, there is no transformation. They don't talk about it. So I'm just asking, what is the importance of it? It's like a construction where they have to draw those angles. And when they go up, that chapter is no longer there. So what is the significance of that one?
I'm not quite sure why you think somehow the transformations are not there. I mean, the thing is, it's an important idea, and we learn about reflections when we're very young, about looking at ourselves in the mirror, looking at shapes like hands which are reflected, and rotations. There's so many applications of transformations in the real world. Screws are a rotational, you know, we use screws and screw thread and the spiral. We're talking about rotations. It's so important in maths. So I don't know, every country has a different curriculum. They put emphasis on different bits of maths. They only learn some of the maths that they might be learning. So it's up to you as the teachers to introduce and spend as little or as much time as seems relevant in your country on the topic, but don't neglect transformations, because Changisa, it is quite important. So different countries will introduce the same ideas for different age groups. And we've only given a rough approximation of how this is built year by year as the learners make some progress on this learning spiral.
And someone says, may we do this over and over again? Fetole, absolutely. Tony and I, this is fulfilling our life's purpose. So we will continue to do this once a month with the 2-hour workshops, and we're looking at doing other things as well. But this once a month 2-hour workshop will be an ongoing thing. So please do tell other people about it.
Thank you for being part of this.
Goodbye. We'll see you next month. It's been an absolute pleasure. Thank you all for your really great participation, and let us know what you do with this.
Goodbye, and thank you very much.
Thank you so much. Goodbye.
Goodbye, everyone.
Thank you.
Goodbye.
Thank you, Tony. I'm happy to see you.
Bye-bye, Lillian. Thank you for your participation.
Thank you very much.